Good. You ready? You're a mean, lean learning machine. We said energy was the ability to do what? Yeah, good. Energy was the ability to do work. If an object had energy, I said it could be apply a force over a distance. I'm going to generalize that a bit more today. Now, we did say that work equals force times distance. This was the easiest way to calculate work. It's also the most useless. It's not useful as often. Here, the force had to be a constant force, and there were some limitations. I also told you that work was the area under a force versus distance graph. So I'll just draw a slanty line and then kind of color in a trapezoid there. I'm not going to be giving you area questions on your quest. I'm planting a seed with this for next year. Next year, we will have to use the concept of area in Physics 12 to figure out cosmic potential energy. What's potential energy when you're not on a planet? What if G isn't 9.8 because you're in outer space? Now what? MGH no longer works. We'll derive a generalized one. So work equals force times distance. Work is the area under a force versus distance graph. The best definition of work, Liam, but also, no pun intended, the most work, the most writing, is the work energy theorem. Work is the change in potential energy and the change in kinetic energy. That's how much work you've done on an object. That's how much energy the object has gained or lost. Oh, where delta is change in, what's change in anything? It's on your formula sheet, the very first thing, top left corner. So I'm going to make a little note where delta means final minus initial. Did I give you that on your formula sheet? In fact, I even think I called it the work energy theorem. I was nice. So let's just jump on in. It says this, example 1. A cyclist weighs 65 kilograms. Her bike weighs 7.2 kilograms. I'm going to pause and I'm going to say, I guess that means M is 72.2 kilograms. I added them together and I wrote that so I wouldn't accidentally use the 65 just because I wasn't paying attention. If she's pedaling over level ground and underline level ground, that's going to be helpful. Elijah, what's this question asking me to find? How much? No, you missed the first, starting with the word here. Keep reading. Okay, how much work, it has asked me to find work, to increase her speed from rest to 5 meters per second. Don't write this down, look up. Elijah, what are they asking me to find? How much what? My first thought, don't write this down, would be that, because it's the least work, no pun intended. It's the least amount of writing. Did they give me a force in newtons? Did they give me a distance? My next thought would be it's the area under a graph. Be stupid obvious. Did they give me a graph? Don't overcomplicate. Did they give me a force versus distance graph? No. Only then, after I'd tried those two, would I say, okay, I'm going to use the work energy theorem. Work is the change in potential energy plus the change in kinetic energy. Liam, what two words did I underline? If you're level ground, is your height changing at all? Is your potential energy due to gravity changing at all? So because we're on level ground, I can say that. Oh, if there was a hill and I knew the height of it, I could include it. What's changing anything? Final. And kinetic energy is a half mv squared. This is going to be a half mv final squared minus a half mv initial squared. Now, v initial is 0, so I'm going to cross out that second term in a second. But this is the general version on level ground. Hannah, is there an m in the last term? Is there an m in the middle term? Is there an m in the first term work? Mass does not cancel. This is why it's harder for heavier people to accomplish a task that a lighter person can do. A heavier person will actually require more energy, more work. In this case, Hannah, from rest, what does that tell me? Which one? So to go from 0 to 5 meters per second is going to be 0.5 times 72.2 times 5. Don't forget the squared, which is what? I think you're going to get near 1,000, a little less than 1,000, I think. 902.5. Anybody else? Units? Joules. So let's talk about what this means. This means the bike and rider combination gained 902.5 joules of kinetic energy. Where'd that energy come from? Because it's got to come from somewhere. Where did it come from? Be fairly obvious. Don't overcomplicate it. Where'd the energy come from? The pedals give us energy? Keep going. Food. This is why you can lose weight exercising. You're burning. Now, the unit for food energy isn't joules. What's the unit for food energy? Calories. Got someone coming in. Let's see. Pause. This person has lost 902.5 joules of food energy going into kinetic. But here's what I want you to notice, Matteo. What did she start at from rest? As a number, what's her speed then? From rest, 0. What did she end at? What did she increase by? 5 meters per second. Look at B. How much are we increasing by in part B? See it? From 5 to 10? B says, let's do the work again. We're going to walk through the same argument. We're going to say work is the change in potential plus the change in kinetic. Matteo, are we still on level ground in this question? So we can still say, get rid of that. If there was a hill, I could work it in, but I don't need to. What's changing anything? Final minus initial. We get the same second line. We get W equals a half mv final squared minus a half mv initial squared. But this time, none of the numbers are going to cancel. It's going to be 0.5 times 72.2, Mr. Dueck, times 10 squared minus 0.5 times 72.2 times 5 squared. All of you want to type that into your calculator. There's a reason. You'll see why on the next question. So if I go to my calculator, yoink, 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. You're not going to get 902.5 joules, even though it's the same increase of 5 meters per second. Maddie, what'd you get? I got 2707.5. See if you get that. What does this mean? Once you're going fast, if you want to go faster, does it take more energy than the previous gap or less energy than the previous gap? The faster you go, the more it takes to go faster. In fact, Maddie, what are we doing in part C? Still a 5? You know what? I'm not even going to write anything down. I'm going to go to my calculator and backspace. I think where the 10 is, what do I want where the 10 is this time? 15. And what do I want where the 5 squared is? 10 squared. Still a 5 meter per second increase. Way more energy. Now we're looking at 4,500. Work equals 4,512.5. This has a huge impact or implication for rockets. Rockets have to go very fast to leave Earth's gravity. To do that, you need a lot of energy. You need a lot of rocket fuel. You know what happens when you add more rocket fuel, Seda? You increase mass. Did the masses cancel in this equation? So now you need more rocket fuel. Oh, you know what happens when you add more rocket fuel, Seda? You increase. Good. Oh, you know what that means? You need more rocket fuel to cover that. It's called the tyranny of the rocket equation. We can barely get out of Earth's orbit. Barely. If you look at a big rocket when it's sitting on the launch platform before it launches, the payload is probably, sorry for those who are on YouTube, it's about that much. See the gap in my thumbs? This is all fuel. If Earth was about 10% bigger, we couldn't leave the planet. There would just, you can run the numbers and show even the best fuel possible, which is the best energy possible, which is Einstein's E equals mc squared equation, not enough to get you off of the planet and out of Earth's gravitational field. We can barely do it. What that means also, by the way, it's possible there could be intelligent life out there that evolved on a planet that's about 15% larger than Earth. They can never have a space program, no matter how good they are, because they can never get enough energy because of this work equation to actually get off their planet and out of Earth's gravity well and to the rest of the universe. Little newsflash. Hey, speaking of rocket science, let's do a rocket question. Example 2. A model rocket reaches a height of 340 meters when launched if the top speed of the rocket is 85. Matt, what's this question asking me to find? Now, my first thought, don't write this down. I would always start there because it's the least amount of work, no pun intended. They gave me a distance, that 340, and I might be tempted to go like MGH or something, but have I incorporated the 85 yet? What is that 85? What are the units next to it? It's a speed. You know what? I think there's going to be some, you know what? I think there's going to be a change in kinetic energy. I need to use the work energy theorem. What's the work energy theorem? It says the change in potential plus the change in kinetic. What's change in anything? So for potential energy, it's going to be mgh final minus mgh initial, and then plus. For kinetic energy, it's going to be a half mv final squared minus a half mv initial squared. I skipped a step, Liam. I didn't write PE final minus PE initial plus KE final minus KE initial. I was bold because it's Friday and you're tired. I put the equations in right away. Hey, are any of these zero? Potential energy is going to be zero when H is zero. Are we ever on the ground? If we launch a rocket, are we ever on the ground? Liam's nodding. When? Initial or final? Yeah, hopefully not final, because if that's the case, something's gone terribly wrong. What about kinetic energy? Are we ever at rest? We're at rest right before we press the launch button. So I'm going to say that we're starting out with no kinetic. Now, once we hit that 85 and start coasting, we will slow down, but we did need that a half m85 squared at one point to hit that. What we're going to calculate is how much energy to put this rocket there. We're actually calculating how much energy the engine has, and from this you could calculate how much model rocket engines use of powder, but how much rocket fuel you would need. Do the m's cancel? Is there an m in everything here? Not in work. So the work is going to be 0.15 times 9.8 times 340 plus 0.5 times 0.15 times 85 squared. How much energy will we need to get from the rocket engine? How much work does the rocket engine need to do on the rocket? What do you get? $1042 joules. Now we're ignoring, is that not right? Anybody, is it 1042? Okay, people nodding, so your typo is with you. We're ignoring air resistance, but There's a reason why all rockets look the same. Why do all rockets look like the same shape? What are they trying to minimize? Air resistance. If you wanted to include air resistance, though, you really need calculus, so no. I like example 3, I like example 3, I like example 3. Example 3 is a nice question. I'm really, really, really giving you a strong hint, 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 hint. Car is traveling at 35 meters per second over level ground. That's kind of important. What's A asking me to find? Jaden, what's A asking me to find? How much work? Work is force times distance. Do you see a force in this question? Do you see a distance in this question? Okay. Work is also the area under a force versus distance graph. Dost thou seeth the graph? We're going to use our third definition of work, the work energy theorem. That's the one that says work is the change in potential plus the change in kinetic. Jaden, what two words did I underline? What does that mean? No change in height. That's 0. In fact, we're going to end up with work equaling, because change in anything is final minus initial, a half mv final squared minus a half mv initial squared. Are any of those zeros? Oh. Bring it to a stop. Okay. We're going to get a negative answer, which is okay. We're going to get negative 0.5, 1250, 35 squared. You're going to get negative and the big number, because a car would have a fair bit of energy it had to get rid of. I think that's right. Can you read me the digits? 76 point something? Okay. Is that right, folks? I think, yes. Why negative? What's that telling me? The car has to what? Lose energy. Does that mean the energy vanishes? No, it's got to go somewhere. That's what the law of conservation of energy. Where do you think it goes? Pardon me? Yeah. What force is stopping it? In our free body diagram, what did we say brings cars to a stop as well as makes them go? It's the same force. What? Yeah, friction. Where most of this energy is going into heat, your brakes are going to get hot. In fact, B. Emily, what's B want me to find? Which force are we actually finding? You know what I think we're finding here? Friction. Now, I might be tempted to say friction is mu times the normal force. Did they give me a mu, a coefficient of friction? No. What did they give me in part B? What's that 82? What did I find in part A as a concept? Starts the letter W. There isn't by chance a version of work that has distance and force in it, is there? The work done by friction is going to be the force of friction times distance. Emily, get the F by itself. How would I move the D over? Yep. It's going to be my answer button divided by 82. Now, you're going to get a negative answer. What's the negative answer telling me here? That if the car is moving forwards, the force must be? If the car is moving south, the force must be the opposite of south. If the car is moving west, the force must be east. So I'm not going to worry about the negative in my answer. I would have to take both. I'm just going to get the magnitude What do you get, Emily, for the magnitude? Sorry? 937? 9337 and change, probably. It's probably some decimals or not. Units, force, newtons. So what was that? Someone say something? Did you use your answer button? Oh, yeah. Okay. Ooh. Huh. What's C want me to find? Hey, what's mu? I don't know. What's mu with you? Um, what did I find in part B? Which force? You know what? I think I would write down friction equals mu times the normal force. I would start out there. What did you say they're asking me to find? Which is what in this equation? Which variable? How would I get the mu by itself? How to move the normal force over? I don't know the normal force. But I'm imagining the free body diagram where on level ground. Do you know what the normal force is going to be the same size as in this case? Jaden. I mean, you're saying when you don't talk. Jaden, I think we can actually say, you know what? That's just going to equal mg. And so we get this. Mu equals friction divided by mg. It's going to be my answer button. I'm going to ignore the negative if it's still on my calculator. Divided by 1250. Is that the mass? I think it was. Times 9.8. What do you got? And I hope I made up nice numbers and we get a reasonable coefficient of friction. I hope. Give it to me to 3 sig figs, please. 0.762. Anybody else? I got 1 knot. I got 2 knots. Units. Yeah, there are no units because it would be newtons divided by newtons. Your newtons would cancel. Now, this is actually a fairly high coefficient of friction. You might get this on road tires on a nice hot summer day when the pavement has been baking for a while. You won't get this on a rainy winter day. So if you were the road engineer and you crunch this, you would have some decisions to make. You would either need to lower the speed limit on this section of road so people would have time to stop, or you would put up maybe a flashing red stop sign warning, not 82 meters, but maybe 150 meters or more in front of the stop sign so that people would know you need to slow down or you're going to be plowing through the stop sign and totaling your car and injuring someone. Pardon me? You wish our highways were like the Autobahns? Some areas they nearly are. I like example 4. I love example. I love example 4. Pardon me? Ah, I must have added this. I got to renumber these. Good question. I don't know if you remember, but in October, when we were just dipping our toe into the physics world, I did a question with you where we looked at a car crash and we had a car that had skidded to a stop and the cell phone had picked up the sound of the skid and we used that to calculate how fast the driver was. At that time, I said to you, we don't have enough physics to get this from just the skid marks because the likelihood of the cell phone voicemail picking up the sound of the skid is so unlikely. I had to make that up so that we had time. I am fulfilling my promise. I told you all you actually need is the distance. Here is how an RCMP crash scene investigator would do this. So an RCMP officer is investigating an accident. The car struck a pedestrian at a school crosswalk. There are no witnesses. The officer measures the coefficient of friction at the accident site to be 0.65. They have a little machine that they drag along the ground and it turns a scale and they can measure how sticky the pavement is given various tire types. So they measure it to be 0.65 and he measures skid marks to be 49 meters long. Should the RCMP press charges against the driver? Although this question asks, should charges be pressed? In terms of physics, what do we ask to find? Distance it took to stop was 49. Velocity, which one? What's VF of every car accident ever? So what? And I got to be fussy. It's speed, not velocity, because this is going to be a scalar, but we can find that. Did I mention I like this question? Did you pick up the hint? My first line, which is so obvious that it's not obvious, argue with this. I would write work equals work. Duh! It's like writing x equals x. Duh! Except now I'm going to use both of our equations. I'm going to say, okay, this is force times distance, and this is also the change in potential plus the change in kinetic. Read the question carefully. Is there more than one height given at all? I think we can assume it was on level ground. If it wasn't, though, it wouldn't be that much tougher to bring in the change in potential. I would just need to measure the elevation change. But for now, what's change in anything? So I can write this as force times distance equals a half mv final squared minus a half m v initial squared. And ooh, are any of those zeros? What's the final velocity speed of every car accident ever? So I think I can do this, which is a little weird. You're going to get a negative answer. Actually, you're not, because this force and this distance are not in the same direction. They're in opposite directions. We would signify that by putting a negative there. My point is this. On the next line, I'm going to chuck all the negatives. I'm going to write this as force times distance equals mv squared over 2. Or you could write 0.5 mv squared. I don't care. What am I trying to find? Okay, I want to get this by itself, and I should have put an initial there. Do I know the mass? Do I know the distance that we were skidding? Do I know the force that brought us to a stop? Okay. Which force? What is that F? What is it that brings cars to a stop and also helps them start? What? Yeah. I still don't know how big friction is, but friction is what times what? So I might, on my next line, say, okay, mu times the normal force equals mvi squared over 2, a half mv squared. I don't know the normal force. Oh, but look. I know the force same size. I think this time the normal force once again equals mg. You okay with that? So what am I going to get? I'm going to get mu mg equals mvi squared over 2. Oh! What do you notice? What about the same as the last one? I noticed something else though. Is there an M in the left-hand term? Is there an M in the right-hand term? Is there an M in every term? You know what that means? Yeah, this is really useful for the RCMP. It means they don't need to know the weight or the type of car that was involved in the accident. Mateo, they can already start their investigation. Oh, and a lawyer, a defense lawyer, can't say, oh, my client's vehicle had a full tank of gas, so it took longer to come to a stop. No. Or my client's vehicle was carrying a heavy load, it took longer for it to come to a stop. No. No. M's canceled. What am I trying to find? VI. Let's get the VI by itself. How will I move the 2 over? This 2 here? Okay. Times by 2, then what? Times by 2, then what? Ah. I'm going to get VI equals the squared. Or instead of a 2, you could have put a 0.5 in front and divide by 0.5. Ben, both of those are acceptable. But I'm going to get the square root of 2 mu g. And I would be willing to bet accident crash investigators that would be an equation in the back of their book that they would just look up right away and use. We did the derivation. They would just have that. I've scrolled down to, what's mu? I don't know. What's mu? Sorry? 0.65? 9.8. How fast was this car going in the school zone? What'd you get, Mateo? Oh, you started to type. I don't think so. I think you get something that nearly tries to work out evenly, but not quite, but I might be misremembering. Sorry? 3 point? Did I make a dumb mistake here, Mr. Dueck? Mu mg, mv squared over 2 times by 2, the m's cancel. Oh, I forgot the distance. Thank you. It's here, force times distance. Jeez, Dueck. I forgot the D. Who said distance? Candy again for you. I forgot the distance in here. So in here, what was the distance? 40? That's going to make a difference. I'm so sorry, folks. Try that. So. I think it's 24.98 or like it's 25 if you try rounding the 3 sig figs, right? 25 meters per second. Sorry? 25 what? What's that in kilometers per hour, Carson? Answer button times 3.6. Oh, yeah, you can charge him. Right? That's around. Well, there's always extension. Now, this because they're speeding in a school zone, probably. I told the story to my last class. Just because you hit a pedestrian, you might not be at fault. I almost killed somebody about 10 years ago. It's one of those ingrained in my life moments. I was driving in Surrey, lots of traffic. RCMP were chasing a criminal on foot, and the criminal, without slowing at full sprinting speed, ran in front of me. And what I remember, I slammed on the brakes. It was close enough. The criminal ended up putting both hands on my hood. Otherwise, he would have bounced off. And he kept going. And the RCMP looked both ways and kept going. But I remember just shaking. I had to pull over and just breathe for about half an hour because whatever had happened, I'd almost killed a human being. And that's not something you ever want to do. Pardon me? No. Really? The death penalty because you were I don't know. Really? I don't think so. And by the way, you don't realize the movies, if you see a movie where the good guy kills a bunch of bad guys, they kind of shrug it off. Thankfully, we are not wired that way. If you kill somebody accidentally or on purpose, out of anger or accidentally, it scars you for life. And that's a good thing. That's why when you lose your temper, you don't suddenly pick up a knife and go. It's just built into us. It's why soldiers coming back from war, they start to realize, oh, those human beings on the other side, they had families like me. They had parents like me. And you have a lot of stress to deal with, which is, again, a good thing. But yeah, this person we could certainly charge. Now, if you see this in the future, hint, hint, I'm not going to say should this person be charged. I'll probably just say find the initial speed. Okay. But this is also keeping my promise. I told you, beginning of the course, we would revisit this at the end of the year. Yeah, I agree. Worth making some noise. Now let's look at some dumb driving. I found this on YouTube. This was posted about 10 years ago from Vancouver Island. Put your pencils down, look up. And we're going to finish with this. I bet you'll find out in about 30 seconds. Look behind you. There's some patience. You might want to help yourself to some. Mr. Dueck, I can't wait. Was this? We're going to get there. Let's separate there. Motorcycle goes fast. I took this because you can see the speedometer, which gives us some numbers, some good data. Why are we seeing the sky? How fast is this driver going? What? Look at the inside speedometer. Look at the outer speedometer. What? Convert 220 miles per hour to kilometers per hour.
The answer is 354.06 kilometers per hour.
But do we do physics with kilometers per hour? What do we want our units in? Okay, so convert 200 miles per hour to meters per second. Sorry, 220. Hang on. Convert 220 miles per hour to meters per second. What do you get? It says 98 point, we're going to call it 100 just as a nice round number. Also because he's pinned the needle, he kept speeding up a little bit. So I'm going to give him the 100 meters per second, which, think about that. That's a football field a second. Can you actually drive that safely and react that fast to anything? No, this is dumb driving. Okay, now, watch. What's our VF in miles per hour? Read it. 100. Convert 100 miles per hour to meters per second. 44.7. Okay, we got some numbers to work with here. Donk. I'm going to assume the mass of the motorcycle and the rider is 300 kilograms. I Googled a few fast street bikes, took an average mass, and then added the average mass of a human being, and then rounded off because we're doing a lot of rough guessing here. So, alrighty. Carson, what's A asking me to find? What's it really asking me to find? How much work was done by the brakes? We're going to use the work energy theorem. Change in potential plus change in kinetic. You all saw the video. Did it look like there was a hill involved there anywhere? That looked like a level road, so we can do that. By the way, for the previous question, this if there was a hill, the RCP just has to measure the height of the hill and include that MGH, and they can still do it. And the M's still cancel wonderfully as well. Just saying. And what's changing anything? So it's going to be work equals a half mv final squared minus a half mv initial squared. Let's make a little note here. V initial was 100 meters per second, right? And V final was 44.7. I'm going from memory, but I think that's what it was. Alrighty. How much energy was lost to heat? 0.5 times 300 times 44.7, don't forget the squared, minus 0.5 times 300 times 100, don't forget the squared. You're going to get a big number. Mr. Dueck, why is the 44.7 V final? Because that was V final, slowing down. You're going to get a negative answer. Why are you getting a negative answer? What's that telling me? That what's happening to the motorcycle and rider? They're losing energy. Doesn't mean the energy's vanishing. It's got to go somewhere. Jaden, can you read me the digits? It starts with a 1, I think. And I think, is it a 1, 2, something, 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 something? Read me the digits. Uh, 1.2 million joules. Ben, what does B want me to find? Where does the energy go when you're hitting the brakes and slowing down quickly? Yeah, which is such a waste. This is one area where both hybrids and electric vehicles have a huge advantage. They bleed the energy off not as heat, but as electric energy, and they recharge their batteries. That's why every taxi cab you see now is a hybrid, because every time they're coming to a stop, they're actually recharging their batteries a little bit. A little bit still goes into heat, but most of it goes into recharging the batteries. How does that work? Take Physics 12. Quick like a bunny. I'm almost done, but quick like a bunny. C. Ooh. Okay. Siobhan, what's C want me to find? Power. What's our equation for power? Yeah, I got that part, Captain Obvious. What's our equation for power? Ah, what did we just find? Work? Oh, this will work. Okay. Power is going to be work over time. It's going to be our answer button divided by, can you get out your smartphones? We're going to use the stopwatch. We're going to see how long it took him to or her to slow down. So get your stopwatch out, and when you hear the engine noise change, we'll start, and then we'll stop when they hit 100 when I say stop. So you ready? Wait for it. Start. How many seconds? 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 Okay, since no one was playing along, everybody get your stopwatch app out, please. I don't think it is. I think all of you are wrong. Are you ready? Wait for it. Start. Stop. Yeah, it's in the 16 point something or a little bit less. We're doing a lot of rounding off, so let's just use 16 seconds as our time. Ben, pardon me? What did I just shut the video down. What did I pause it at this time? Well, oh, did I stop it too soon last time? I'm so sorry that I'm dumb. I went to, because 100 was our final. Sorry. I lost my prep today. I had to teach grade 8s. I'm tired. So 16, answer button divided by 16. Ignore the negative. It's a power loss. That's what it's telling us. How many watts? Spoiler, also going to be a big number. I think it's in the 70,000s, but it will ignore the negative. Just read me the digits. 75. So I'll go 75,020. Power is measured in watts. That's tough to quantify. So, what's D want me to find? Hannah. Take your answer, divide it by 60. How many light bulbs could we run from this? How many motorcycles does it take to to power a light bulb? Or how many yeah. Yeah, you're going to get something like that. Yeah, use your answer button. You're going to get about well over 1,000 bulbs. This is why, honestly, no matter how much you like internal combustion engines, in terms of efficiency, electric engines with a regenerative system that bleeds this energy off back into charging the battery is the way to go. Pardon me? A little bit, nowhere near with the efficiency. My friend has a Chevy Volt, and many times he's been at the top of the Coquihalla. He looks at what I got 65% battery. When he gets to the bottom an hour and a half later, I've got 91% battery because he's losing potential energy. He's got to go somewhere. Goes into recharging. Teslas have regenerative braking. Oh, yes. Have you driven a Tesla? So if you drive it, you don't actually hit as soon as you take your foot off of the gas pedal, it starts to slow down. That's the regenerative. In physics 12, I'll teach you you're generating a back EMF and you're actually generating a voltage in the opposite. The wheels start acting like generators. Yeah. No, but yep. Yep. Example 4. Yeah, right now I think we're finding often, depending on the climate, up north not as good, but the batteries seem to be lasting a little longer. And I'm sure you've read they're spending billions around the planet for battery research because whoever gets the first breakthrough, whoever can make a battery that can hold a lot of charge and recharge in like 15 minutes, that'll because it takes me 10 minutes to fill up my gas. 15 minutes for electric, I'd be willing to do that. I'm not losing all that time. Grab a cup of coffee and I'm good. Anyways, you can cross out number 4. I'm not going to ask you questions about force versus distance graphs on your quiz. I planted the seed here. I gave you a couple of questions in lesson 1. We're going to see it way more next year. You can try number 1. You can try number 2. You can try number 3. That's it. Put your pencils down, look up.
The new Boeing 747-8 is a massive machine, designed to take off at close to 1 million pounds. Through months of flight testing, the airplane has shown plenty of power on takeoff. But how would it handle all that energy if it had to suddenly stop?
They're going to practice what's called an RTO, a rejected takeoff. The theory is the plane has hit takeoff speed and, oh my goodness, something just wandered onto the runway. But they're going to do it in worst case scenario. They're going to have as much fuel on board as possible because the M's did not cancel in our work energy equation. They're going to shave the brakes down to basically 0, so no brake pads. And normally planes can reverse their engines to help them stop. They're going to pretend that the engines have died so they can't use reverse thrust. So all of the kinetic energy is going to go into heat. How much heat? If you watch close, you'll see the massive wheel hubcaps glowing orange hot.
Emergency event that we have to make a rejected takeoff at these heavy weights. It takes a long distance for the airplane to stop. It's just like in your car.
Captain Kurt Vining and the Boeing Test and Evaluation team are about to put the airplane through the ultimate rejected takeoff, or RTO. First, the crew installs a set of 100% worn-out brakes.
So it's down to the stud. So if you ever have your own brakes, they've got them machined down so there's just basically no material left.
Technicians also fuel the airplane up to maximum takeoff weight of just over 975,000 pounds. At the start of the runway, Captain Vining begins the takeoff roll as usual, pushing all 4 engines to maximum thrust. But just as the airplane is going at over 200 miles or 320 kilometers per hour, he slams on the brakes. To channel maximum energy to the carbon brakes, the pilot cannot use the thrust reversers.
The whole intent is to demonstrate you, under worst conditions, you could safely stop the aircraft.
The brakes, made by Goodrich, do exactly as they're supposed to. In fact, the 747-8 stops earlier than the team had hoped,
But there's a lot of heat that's just been generated.
beating the target by more than 700 feet or 200
Yeah,
meters.
blowing.
But stopping is just half the challenge. Now the
Blowing
airplane
orange.
must prove it can withstand the
Blowing
tremendous
orange.
heat that built up in the wheels, estimated to be more than 1,400 degrees
Blowing orange.
Celsius.
Blowing
And it's
orange.
a simple physics problem. We have to turn that kinetic energy into heat in the brakes.
Yep.
As expected, smoke pours out from the brakes as they glow a bright orange. Still, the firefighters who are standing by can't do anything but watch.
Why do the firefighters just watch? No. We want to simulate in real life, would the firefighters be there right now? So they're setting their stopwatches. On average, it takes about 5 minutes, so they're going to wait about 5
For the
minutes.
next 5 minutes.
And that's to simulate that if you were at an airport, you had an RTO, you wouldn't necessarily have the fire department right there. So you demonstrate that worst case would be 5-minute response time for a fire department to get to the airplane.
By design, special fuse plugs in the tires are activated, deflating the tires before they explode.
Why might they explode? Yeah, the air is getting hot, so they've thought of that. They have some fuse plugs that deflate them slowly.
Finally, at the 5-minute mark, firefighters move in with plenty of water. While the tires and brakes will have to be replaced, the rest of the airplane is perfectly fine. No sweat, even for the flight test engineers who were on board.
It went amazing. The decel rate was exactly what we expected. Great stopping, no major faults.
So that's kinetic energy being turned into heat. You don't always have to turn it into heat, though. Here's a physicist from Sweden who's standing in front of a loaded rifle aimed at himself, and he's about to pull the trigger. Where is it, Mr. Dueck?
Skudd kommer. 3.
Now, underwater, but he's standing in front of a high-powered loaded rifle. Now, he's run the numbers a bunch, but another way to bleed off energy here, it wouldn't be heat, it would be the force you're applying to all the water molecules to move them out of the way.
2. 1.
Oh, I was too slow. You can see it goes a little more than a meter. In fact, you can see he's probably tripled the distance for safety. Even though you trust your math, you're not going to muck around with this. But could you dive underwater to escape bullets like they sometimes show in the movies? Ish, you've got to get fairly far down. Hey, how can a gun fire underwater? Doesn't it need oxygen? No, all modern ammunition that's used in warfare, they've thought of that. Otherwise, in a downpour, your gun might not fire. They've got oxidizers built into the gunpowder, or you might actually need to fire a gun underwater in a war. They've thought of that, so the guns fire underwater. Then, bullet lands on the ground. And that look right there is, I did the math right. I mean, he's got an interesting channel. He's done a few things where he said, I'm going to trust the physics, work out the physics, and I'll do a life-risking experiment. Don't try this at home yourselves, please. Folks, you got about 8 minutes left. If 3 questions, no homework for the weekend if you play your cards right. Carson, you were saying that you'd seen the video. Send it to me, please. Hit the wrong button on my remote. Thank you for your patience. Hopefully you learned a lot.